Let's talk a bit more about impulse momentum. Now, this is the second presentation on impulse momentum. The first one is simply a derivation of impulse equation and momentum equation and the impulse momentum relationship together. But this is a little bit deeper talk on why this is an important concept to understand and ultimately use when we start doing performance analyses. So the impulse momentum relationship is all predicated on understanding Newton's laws of motion. And you've had a presentation on this, but it's good to always go back and review this. So first law of motion is really an observation, a law of uniform motion. Every object continues in its state of rest or of uniform motion, which would be constant velocity, in a straight line unless a force changes the motion. Simply an observation. If something's moving, it's going to continue to move in that constant velocity. If velocity is changing, that means there's a force applied to the object. If the object's not moving, has zero velocity, and it's not going to start moving unless something causes it to change movement, that's a force. The second law is really a definition of what that force is. So law of acceleration. The rate of change of motion, the rate of change of velocity, which is ultimately acceleration of an object, is proportional to the force applied on the object, the magnitude of the force, and the direction and line of application of force. So whatever direction I'm pushing on, that tends to be the direction of change of motion that we're ultimately going to have. Now here, mass isn't in this definition, but other texts will say the rate of change of momentum in this definition. And then momentum, as you'll see, is mass times velocity and actually captures that mass object. And what other texts will do is they'll say the object is proportional to the force applied and inversely proportional to the mass, things like that. But this is the equation F equals ma. If we add up all the forces acting on the object, we can understand that object's acceleration, mass being the object and acceleration being the acceleration of the center of mass of the object. So that's really a definition of what a force is. The third law is really Newton's law, law of action-reaction. And in this law, it stated that for every force applied on an object, there's an equal and opposite force created or applied by the object. When we do our kinetic analysis, it's very important that we only concern ourselves with the on forces, the forces acting on the object. There are times that we're interested in the by force, but we get that understanding by understanding the reaction force being placed on the object. All right, so this is more the law, and we'll continue to work on that, understanding that law at a deeper level. So here's Newton's second law, F equals ma. Forces add up all the forces acting on the object, and we get the mass, the product of mass of the object, measure of inertia, resistance to change motion, times the acceleration of the center mass of the object. Inertia means hard to get something going or hard to stop it when it is moving. F on is a force acting on the object, units of newtons, or remember the base units are kilogram meters per second squared. Mass of the object and units are, add that in, kilogram, units of mass. Measure of inertia. Inertia is an object's resistance to change motion. It's quantified by measure mass. Oh, there, I've got units down here. Units are kilogram. And I do have a separate video on derivation of the impulse momentum relationship, where I start at Newton's second law. I insert the equation for acceleration into the second law, and then I do a little bit of algebra, and I end up with F delta T equals delta mv. F delta T is what is known as impulse. So in a test question, and the question is something like, which of the following is the equation for impulse, you would put down F delta T, or you would select the equation F delta T. If the question is, which of the following is the equation for momentum, it's important that you only pick the equation that says mass times velocity. Okay, the delta mv is a change in momentum. Momentum itself is mass times velocity. It's the product of mass times velocity. Our units for impulse are Newton seconds, and our units for momentum are kilogram meters per second. And again, this is a separate video going through that in more detail. So that's our equation, F delta T equals delta MV, or MVF minus MVI. All right, so why do we need to know this? Or why is it even important? Well, it's good to even just think about a simple movement like this, or landing from a jump. Why do we even do knee flexion during landing from a jump? And why do sometimes we have lots of knee flexion and maybe other times we don't have much knee flexion at all? And why would maybe not using the correct amount of knee flexion, maybe that's a bad thing. So let's think about that from an impulse momentum relationship. And let me keep going here. I got another example here. Let's look at throwing and catching a ball. This is probably a little easier to see in terms of impulse momentum. Impulse is the force, the magnitude of force times how long it's being applied. And you can see here in this series of pictures that force is being applied to the ball over several frames of this image. The longer that force is being applied, the greater change in momentum that ball is going to have, because F delta T equals delta MV. Let's go back to this situation here. The force acting on this person upon landing on the ground is the ground reaction force pushing upwards. The person is pushing down on the ground, and ultimately that's a force that we're interested in. But when we do our kinetic analysis, we only identify the forces acting on the person, not by the person. But the ground reaction force is equal and opposite to the force created by the person. So if you think about the magnitude of force that's going to be applied here, if the person uses more or less knee flexion, maybe we can start to understand the importance of this impulse momentum relationship. The person needs to stop their downward movement. That's going to be a stop of a change of momentum to zero momentum. And you can do that either with a smaller force applied over a longer period of time, or a bigger force applied over a short period of time. So if we go through lots of knee flexion, we are in essence decreasing the muscle force peak magnitude, but applying that force over a longer period of time. If we land with less knee flexion during the landing phase, we actually are going to have to apply a greater force over a shorter period of time because we're doing less knee flexion. So that's going to be a very stiff landing. Now you would say, well, why don't we always just pick the right amount of knee flexion? Well, sometimes you can't. Sometimes you're restricted based upon maybe the sport. Think about basketball and rebounding a ball that the player needs to get. The player may not have time to land in a way that is optimal at reducing the magnitude of force on the knee extensors. And instead, that player may need to land from a jump and maybe immediately jump back up to rebound a ball. And so that delta T of that jump becomes really short, which means to change momentum, in that case, you're going to need a lot more force. You're going to have a high magnitude of force. Maybe you get to a point where that high magnitude of force is actually causing an injury. All right, and same thing here. This person does not need to be taking that initial step, but by taking that step, they're increasing the time that they're applying a force. If they want to reach the same change of momentum of this yellow ball at release and not include that first step, they're going to have to apply a much greater force over a shorter period of time. We can also think about catching this ball if the ball's coming in and this person's catching it. If you reach out and you catch the ball and then you go through elbow flexion and maybe even taking a step backwards, like we're playing this in reverse, you're increasing the time that the force is being applied, and therefore you can decrease the magnitude of force to get a change in momentum. If you reach out and you catch something and you don't give. You don't go through elbow flexion. Well, now you just need to create a bigger force applied over a shorter period of time to get that same change of momentum. Okay, so what's important here is the impulse causes a change in momentum. And therefore, we can have a change in a given change in momentum by either having a bigger force in a shorter period of time or a smaller force in a bigger period of time, because it's the product of those two. Impulse is the product of force and time. And our units are Newton seconds for impulse and kilogram meters per second. So here, just to emphasize that point, impulse is the product of force and how long that force is being applied to the object. The longer that blue arrow is being applied to that yellow object, the greater the change in momentum, starting from zero momentum to something at release. If you can increase that delta T, you can increase the delta MV. And if we play this in reverse, and that person's catching the ball, the same principle applies, that to change the momentum from something to nothing, we can do that either with a lot of force applied over a short period of time or a smaller force applied over a longer period of time. I did the unit analysis in the other presentation, so I won't do that here, but it is important to know that we associate Newton seconds with the units for impulse and kilogram meters per second for units of momentum. They are the exact same units. It's just better to say impulse units are Newton seconds and momentum units are kilogram meters per second. All right, so now let's take this even deeper where we actually measure some forces. So this is the anterior posterior ground reaction force during the stance phase of running. What do we have here? This is the y-axis, and this is the anterior posterior ground reaction force magnitude, and the x-axis is time. This point is where the foot contacts the ground, and this point is where the toe leaves the ground. So this entire period, the foot is in contact with the ground, no slipping, no sliding. And what we have here is a period where forces are negative. So the person is running in the positive direction. So this negative force is a force pushing in the opposite direction that the person's moving. All right, and so this force is actually causing the runner to slow down. At some point, the force transitions from a negative force to a positive force, usually around mid-stance if the person's trying to run what we would say is a constant velocity. And now these forces are, or this anterior posterior force is positive, meaning that the force is now in the same direction as the direction of movement. It's actually causing velocity to increase during this period. So what we have here in this shaded region is some slowing down of the person because this force is pushing in the opposite direction of movement, and then some speeding up because this force is pushing in the same direction that the person is trying to run. So a question becomes, can you figure out, is the person slowing down more or less than speeding up? And is the velocity at the moment of time zero, when the person's running and striking this force platform, is their velocity at that moment in time greater or less than the velocity at takeoff? You can actually answer this just by visually looking at this plot. The reason for that is that the area under this curve represents impulse. And when I say under, what I mean is the area closer to zero. So this shaded region is actually under this line because it's closer. This area is closer to zero. The area here would be the area for this region of the curve. And why is area related to impulse? Well, impulse is force times velocity. And if we thought of this as just a rectangle, the height of the rectangle would be force, and the width of the rectangle would be time. So that's F delta T. That's momentum. Or excuse me, that is impulse, and that is the change in momentum. And there's some techniques that we use to calculate this when this curve is a curve and it's not a rectangle. We can actually still get a good understanding of what the mathematical area of this shape of curve under the what that magnitude of area is. And you should be able to visually see that the area here in the shaded region is just bigger than the area in this region. That means the change in momentum in this region is greater than the change in momentum in this region. That means there's more slowing down of velocity during the stance phase of gait for this example versus speeding up. That means the velocity, whatever this velocity is at the moment that the person strikes the ground, maybe it's 3 meters per second. When they leave the ground, it's going to be less than 3 meters per second. And you can pick that up simply by looking at this relationship between this area under the curve here versus this area right here. Now, when we do a research project and we ask the person to run with constant velocity, you would think that this would be a zero graph, but that's not the case. Every time you strike the ground, you will always have some braking forces and you'll always have some propulsion force during the stance phase of gait. One trick, though, is to try to minimize the amount of braking to then therefore minimize the need for more propulsion to maintain a particular velocity. So we try to work on a running style where the braking impulse is the same as the propulsion impulse. All right, but I did this as an example to start demonstrating that the change of momentum would be greater here in this region up until this moment of time than the change in momentum in this region here. Okay, impulse, the product of force applied and the length of time applied. The equation is F delta T, the units are Newton seconds. Momentum is the quantity of motion. The equation is M, mass of the object, times velocity of the object, and the units are kilogram meters per second. Same set of units, but really we say Newton seconds and kilogram meters per second. And this is really important. Impulse causes a change. Let me bold that, underline it, and italicize it. Impulse causes a change in momentum. F delta T, mv. Okay, that's just a little bit more on impulse momentum. Thanks, everyone.